Okay, so let's continue the Lagrange multipliers on another examples in which now we are focused that the Lagrange can be also used for two constraints. So this means you have f, which is your surface functions, and there will be another two functions or equations, which is g and h, which will be your constraint. So the constraint will be on these two, which means because of these two constraints, we have two Lagrange with different symbols. So the first one, let's say we are writing lambda. The second one is u. Okay? So we have two Lagrange in the system of equations that we might need to solve this. Depends on the functions and it depends on the system of the equations. Remember what this called the del. Del means it's a vector. Vector means this will be consist of three. If this is three variables, we have three different axes, right? So which means the del f is a vector. In x-axis we have partial x, partial y in the y-axis, partial z in z-axis. Okay? And this will be, I think you are going to learn more in factor calculus in engineering of mathematics. There will be some sort of applications. I think you're supposed to learn this del in physics when you learn the electromagnetic field, or not? Yeah, because this is basically the del F is what we call as a factor field that can describe gravity or electromagnetic field. Okay, this is an expressions. I think if you see the picture, you'll see that at certain points, like all this plane, they will have some intersections. They will cut out each other, which means that at certain points we can find they are going to be in the exact same location, right? Which means that we can have this expressions as true and confirming this all the plane. Okay. Okay. Anyway, so basically, so in geometrically, if you would like to write some notes here, let me write. So geometrically, we want to find extreme values of f, that is our surface functions, when the xyz restricted on curve of intersections. Let's say we have C of the level surface G. So the curve C is the intersection between G equal constant and H. Which we can turn into our Lagrange multipliers equations. And at this moment, we are going to see that the delta F is orthogonal to C at P. So right here, the del F is orthogonal to C, and del G is also orthogonal to G, and del H also orthogonal to the XYZ, the level surface. So we say that the del G and del H orthogonal to this C, which means this we need to solve each one of the axes. I think let me just go to the example, okay? To the example. So suppose that we have a function and we have a two constraint that is going to be intersect with one another. Plane x minus y plus c equal 1, x squared plus y squared equal 1. So that's the two restrictions or two constraints. So we can write the del f is lambda del g and plus mu del h. I will write in terms of factor like this. 1, 2, 3. I think this is very simple sampling. And del g is 1, negative 1, 1, plus mu is 2x, 2y, 0, right? And then we can equaling each one of the axes. So 1 equal lambda plus 2x mu, 2 equal negative lambda plus 2y mu, and the last one is 3 equal lambda and nothing. So immediately we get that the lambda is 3, okay? And then we have constraint. So let's solve this lambda 3 and put into the informations. So continuing that this will be 1 equal 3 plus 2x mu. We get 2x mu is negative 2. So x is negative 1 over mu. And similarly for the y, two equal negative 3 plus 2y mu. So 2y mu is 5, or y is 5 over 2 mu. So we have these expressions. Notice that we have the constraint without any z variable. That means we can plug in this x and y and compute for the mu. Okay, so we can write down So we have now 4 mu squared equal 1. So we can solve this and become 29 over 4 mu squared. And mu will be plus minus half square root of 29. So which means we have two mu. So when mu is positive, then x will be 2 over 29 negative, and y will be 5 over square root of 29. When mu is negative, x will be positive, y will be negative. Okay, and then we have z, which is derived from this one. So let me write here that z is 1 minus x plus y so we can have all of this. Z is 1 minus that part. So 1 plus 2 plus 5. So 7, right? So 1 plus 7. And this will be equal to the second one is negative 7, right? So 1 negative 7. Okay, not yet finished. The last part is we have now all the x, y, z, right? So this 1 point, second point. So we need to check this possibility for which one is the maximum value. But since we have the x, let me write fxyz is x plus 2y plus 3z. So this is, let me write this is 1, this is 2. So checking both of them, we are going to get either 3 plus square root of 29 or 3 minus square root of 29. You can just plug in and multiply. We will get the maximum value is actually 3 plus square root of 29. Okay. Let me write like that. Okay. Compute. Okay. So Lagrange method finish. Maybe we need to have some familiarity and exercise. Maybe we can try 1 or 2 example or from the textbook exercise. Okay, I think we can try for some exercise, right? I think we can start from a simple one and then the one that's a little bit complicated. Okay, let's move to some exercise. I'm preparing, I think, just two kind of questions. So let's try the I think we could try maybe number 7. Number 7. Okay, so try number 7. So number 7, we have f 2x squared plus 6y squared, and we have a constraint. Okay. So if the question doesn't specify the method, basically you can use whatever method. But if it is given, you have the functions, you have some restraint or restrictions or constraint or another function that has some constant value, which means that you can try the Lagrange. But how about if we are not using Lagrange? Basically what you are going to do is you need to find the critical points like the previous method. You need to find the critical points. Partial x equals 0, partial y equals 0. You get the critical points. You check the second derivative test. You check the fxx, fyy minus fxy squared. If you have positive value, it can be minimum, it can be maximum. You need to check again the fxx, check the points. And then if the d is negative, it will be the saddle point. Okay? That must be a very fundamental principle in the maximum minimum value. The Lagrange is another method to get the maximum minimum value from the constraint. So when we get this, we can partially derive this. Okay. So if you see this type of questions, if you are maybe confused on how to do it, the very first step, you take the partial derivative. And I hope you are able to do that with ease. Okay, if you're still finding it difficult to derive this partially, I think it will be very difficult ahead. Okay, so let's partially derive this. So we can write down the del f as 4x and 12y, like that. And remember, when we partially derive, we are creating the factor, right? And then suppose that this is g. So let me create another function which is g. And let me write the del g is 4x cubed and 12y cubed. Equaling this and then multiply with the lambda. We get, I will write directly for each axis. So partial x is, or let me write directly, 4x equal 4 lambda x cubed, and then 12y equal 12 lambda y cubed. Okay, so we have these two equations. Now how to solve this? Remember, do not cancel, okay? Because we are going to eliminate one possible answer or one possibility. So let's move this to the one side. or let me directly write as x and then 4, or let me write this 4x. This is 1 minus x squared, right? So we get that one of the possibility is x is 0, or where's my lambda? Oh, here. Okay. So lambda or x squared is 1 over lambda. Okay. And the same thing with this y. So we have 12y 1 minus lambda y squared. Y is 0, and so y squared is, okay. Now, look back what we have in the equation. We have x to the power of 4 plus y power of 4. So we have power of 4, power of 4. It's a positive function, right? So if x is 0 and y is 0, then they will be contradict the equations, right? So we can write here that x and y both cannot be 0, right? So if x is 0, so if x is 0, then from this equation we get that y will be plus minus 1 over, not cube, sorry, 4, 3, right? If y 0, the same thing here. If y 0, then x also the same, plus minus, or let me write x with power of 4 is equal 1, so x will be plus minus 1. Okay. So we could have possible points for extreme variable. If you want to write maybe clearly, you can write the table, okay, to make it clear the points. Okay. So we can have 0 and plus minus this, or we can have plus minus 1, 0. So we have 4 points, okay? If this is plus minus, so we have 0 plus this, 0 minus this, 1, 0, and negative 1, 0. So 4 points, okay? So we have these possible points. And then what's next is it's not solved yet, because we still have this one, the 1 over lambda, okay? That is still if x is 0 or y is 0, we have these possible points. Now if x squared is 1 over lambda, okay, so because they are equaling the 1 over lambda, so we know that So let me write here, x squared equal y squared equal 1 over lambda. Now the equations then give you which means that this will be 1 over lambda squared because it's power of 4, because it's already x squared in the beginning, plus 3, 1 over lambda squared equal 1. Okay. Then we need to solve these equations. So we have 4 over lambda squared. So lambda is plus minus 2. But if we check lambda, if or maybe checking -2, this will result, because it's already in x squared, this will be imaginary, right? This will be a complex. So this will be non-real solution. So we can skip. So we considering lambda is positive 2, which means that the x equal y equal 1 over lambda, or 1 over square root of lambda. So 1 or plus minus. Okay. Checking back through this part, first part, right? So we have this. Then another possibility is or plus minus so we have 8 points. 1, 2 points, 2 points, this is 4 points. We split this plus minus, all the possibilities. So plus, minus, minus, plus, 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 minus, minus. So 4 points. So after this, check the fxy. Fxy is 2x squared plus 6x. Okay, checking back to this part. And since it is a squared, it doesn't matter positive, negative, right? Because basically we are squaring makes them positive. So we can focus, I think we can check this one, since it has this. And we can immediately remove so this will be square, so 1 over square root of 3. I don't think this will be max value. But if we have this, if we square it, it will be half. So it's quite larger than the 1 over square root of 3, right? So half, I think this will be the max value. And the minimum value will be either this or this. Okay, we need to check. So if we check this value first, this will give you 1 plus 6 and 4, right? And if we check this will give you 2 over square root of 3 plus 6, 1 over square root of 3, or it's 8 over square root of 3. So it's still we get around a number, some number. But if we check the plus minus 1, 0, this will be only 2. Oh wait, this is wrong. I'm writing this is 0. And this is 2, so this will be the maximum. This will be the minimum. Okay. Okay. Any questions? This takes a lot of time. But idea is you need to solve the del system. The del have we call the lambda del G. We're solving that system in any way possible. Use all the means in algebra and system of equations. And whenever you have like possibility, like this one, you have possibility, you need to check out whether they are make sense in the system or not. For example, this part here, we can have a lambda positive, negative, but if we check the system, it will not be allow you to have a negative because on the square, it will be having imaginary number if we choose negative. Okay. Okay, with one more sample, and then we can continue. I would like to try this 30 to 33 for 2 constraints, but I think we need to recheck this again from the number 3 to 10. Because I still feel you are going nowhere. Okay. How about we try to reduce the complexity and try number 5. Okay, number 5. Try number 5. I will give you a couple of minutes to try. If you don't have a clue how to start, okay, then I know where's the problem. Because I think a few of students feel some part is very fast. It's because you didn't catch up the previous one. Because when we move on, especially chapter 14 and 15 later, if you don't catch up from the calculus 1, then you will find it difficult to pass through. And if you still not solving your own problems, I mean, how to start the study and then how to try your best to solve the exercise, it will be very difficult. Like I know, like I think half of the class will feel that if the one that being taught is maybe hard to catch up, then you need to, beside the class, you need to catch up on your own. Like reviewing the previous works will be very, I think that will be my suggestion to review. You don't only need on calculus. You still, I think you need to still to take the engineering of mathematics, which basically is calculus part 3 and 4. So if you think, oh, I'm passing calculus, but you are going to still need some parts of it in the future, at least for engineering of mathematics, you will learn differential equations and alternative methods to solve. And you will learn another part of this del in the vector calculus. Okay, so number 5. How to start solving this number 5? How to start? How to start? Well, remember the principle, the del equal both of the functions, and then don't forget to multiply the Lagrange. Just use the principle, the del equal the other del, multiply the lambda. That's it. And then just solve the system of equations. The partial derivative is just in between. It's in between. I'm not expecting you to solve until the very end. At least until the middle part, it's, I think, still good enough. It's still good enough. So the first part, derive, okay, partially derived. We have f, which is our, so f, if you are given the Lagrange question, the surface function, or the f, usually, it's your functions to be maximized or minimized, the extreme values, okay? So focus on that. We'll give you the del f, so we can write the del f, which is for x is y, for y is x, right? And then suppose we have g is 4x squared plus y squared. Okay, so our del g is 8x and 2y. Okay. So from the del f equal lambda delta g, we can sort of write y equal lambda delta x, and x is lambda 2y. And then simplify these equations, we get that lambda is 8x over y, and also equal this x over 2y. And also don't forget that because of we have this constraint, let me write the constraint. We cannot have, if x is 0, then y is 0, right? Because of the first equations, the xy. So if we look at this xy, if x 0, then y is 0. And if y is 0, then x is 0. So which means that x is not 0, y is not 0. Okay, we need to also write this for the first part. Oh, this is wrong. It's supposed to be y, 8x, okay. Okay, I think I made a mistake for the lambda before. This should be y over 8x. Okay, we will have a break and continue after this. Okay. Finish this part and continue to the next session. Okay, so we have the lambda. Okay, so we have the lambda and we can solve this. Now we can cross multiply. Okay, now we can cross multiply this and we take this as this. So why we can cross multiply? Because we eliminate the chances for x or y equal to 0, right? So because it's impossible to be 0, then we can cross multiply. So the previous question, we can cross multiply because there is a possibility that x or y is 0. So here, since we established that it's not going to be 0, then we can take this cross multiply and get this, right? Okay. Just a basic algebra. And then we get y squared is 4x squared, which we can see from our constraint, okay, that we can substitute to the constraint. Then we have 4x squared plus 4x squared is equal 8. So x squared is 1, or x is plus minus 1. So we have x plus minus 1, right? So if x is plus minus 1, then y will be, so we can just plug in. So plug in, so 4x squared plus y squared is 8. So from here, 4x is 1. So y will be, y squared will be 4. Or this is basically, we can use both of them because they will be the same value. So y will be plus minus 2. So we have 1, positive minus 2, and 1, or negative 1, positive minus 2. So we have 4 points. Okay. So this is the possibility of the values. So possible point. And then check the points. If we evaluate, and we get that max is when f is plus minus 1 plus minus 2, or should be 1, 2, or negative 1, negative 2. This will be 2, and minimum is when it is this or this. So we get the max and min value. Okay? So this is number 5. Okay, so I think that's some exercise. So let's move to the new chapter. Okay, new chapter. I'm providing you with another examples and practice. I hope you can try later. I will put the notes later on. Okay, so we have this exercise here, which is, I think, pretty challenging. If you want to try, this is also another exercise that I hope you could try. But if you are maybe want to start from the simple one, you can start maybe checking out this Lagrange first, or checking out the one that I have previously set up also for the maximum minimum value. Okay, you can check this out, and then after you take on several questions from that part, you can go for this, or this. Okay. Okay, so it's pretty challenging. But now let's move for a while to chapter 15, okay? Multiple integrals. We're going back to review chapter 40, maybe Thursday or maybe next Tuesday, okay? So let's move the multiple integrals. Okay, so before we going into deep, let's recall what we know about the integrals, okay? And how we review what we know. Okay. So first of all, in calculus 1, we have a integrals. For example, I'll just write the basis. So this is what we call as, in visual, this is area under the curve, right, f of x, from x equal a to x equal b. Okay. So this is representations in visuals for integrals. We can also draw this as, suppose that this is f. Okay. The actual integrals is basically, we're going to cut this a few pieces, like very small pieces. And the width, we call the width as a delta x, or simply we can write directly the x because it's very small. And suppose that we are going to take from x equal a to x equal b. So basically, if we are compute or sum or adding all the rectangle components under this curve of f, this is what we call as the definite integral, right? The definite integral. So, and in terms of definition, we can write definition based on the summations, or we can call this the Riemann sum, definition by Riemann. Okay. So this definition says that if we cut the rectangles like with many pieces, if we cut the area under curve, making the rectangle pieces a lot of pieces, large and large as possibly as it can be, it means that we are actually integrating from particular point until the particular point, or from A to B, or that's integral. Now, in calculus 2, in our course, we have a surface functions, right? Which we could see that sometimes we are visually draw like this, okay? Which means that in a sense, if you see what we are actually getting, it's not the area, but it's actually a sort of volume. Okay. So in calculus 1, you get the area, but in this, we call in this surface functions, the area or the one that is under the surface will get into geometrical shape in volume, right? So in the sense that the volume, so this will be getting up a volume. We can write some notes here. Given the fxy continuous, and suppose that we say it's non-negative, okay, on region R. Region R is basically the projection from the surface onto the xy plane. Then the volume between the z, or right, z equal fxy and xy plane is, we can write as, the volume is area of R multiply the height, right? Which is, the height will be the surface function, okay? Or fxy. Suppose that the area of R is getting the same treatment as in calculus 1 when we did this. So we have, it's actually a lot of cutting here, right? Okay, we do the same treatment, but now since we are having the volume, we are going to cut into pieces. Okay, but first let's just see our projections in R, which means that we are going to get this cut. Okay, there's many cuts from the R, and suppose that we take a sample points in between of this sampling, this small rectangular, and we are going to take this sample. So we take the small area here, and we say that this will be our delta A, the small part of the sampling. So which means this delta A will be having the same treatment as in our calculus 1. We are going to, later, we are going to, like when you play Lego, you know Lego, right? You can make a building, right? You can find the smallest pieces. And suppose that the small pieces is the same in the shape. The width, the height, the length, they are the same. So that small pieces, suppose that this one. Okay? So we are starting to build a Lego and make the volume. Okay? So that's if you wonder what it is. So from this part, suppose that we have the delta, or let me write the R first. Okay. The R, suppose the R is from A, B, and C, D for X and Y. So the region R, let me write here, is basically start from A, B in X and also start from C to D in Y, which we can also write in terms of mathematical notations. Because sometimes if I'm starting from this notes, you will get dizzy, right? Sometimes you will get dizzy if you see the math notations. So I will start from the picture first. Okay. And also the height, let's say S, it will be 3 variables and in 3 dimensions, and it will be, we can write something like that, and the xy is real number. So suppose that this small rectangle, we call this is the delta A, that is delta x multiplied with delta y. So this area will be going for this delta A here for area of R. So the volume is delta A, let's say I, smallest one, and multiply with F. Well, it's actually ij because we have 2 variables now. Or maybe for delta A, let me just write delta A as it is. Confusing if I write aj. And suppose that this is the sample point. Okay, so it can be anywhere in between for the location of the points. So basically, if we add all rectangles, then the volume is actually, we have 2 sum. The first one is for I, the second one is for j. This double sum means for each sub-rectangle, the small pieces we take, we evaluate the f at the point and multiply by the area of the sub-rectangle, and then we add the results. So this is what it means. Let me write this, I think, a little bit here. So this is our goal, actually, from the small pieces that we found. Now we have rectangular volume, right? And then we add all of this. We add all. So we add all this stuff, which means the delta x multiplied with the delta y, but we add all. So which means that we add the sum, okay, for each one of the delta, and then we add. Oh, I forgot the delta A. And then, as you may I think predict that the volume, because we can cut as small as possible for each delta x and delta y, so we can say that the limit for m and n is going to be larger. And the sum, we have the double sum. So this is the expressions to define the volume of the solid that lies under the graph F. Okay. So this is volume of S under graph F. and above R. Okay. So we have the definitions for this volume by taking the limit for this double sum, which means it's pretty much similar to the calculus one. The limit and the sum will be the definitions for the integral. So we have the double integral of f over the rectangle R is, we can write double rectangle, and simply you can write R first, because it can be any number, as long as it is going to represent the area. Okay? It's equal to the limit of this double sum, okay? And it's the height, and this is the area. So we call the function f integrable if the limit in definition exists. And we know that all continuous functions, they are all integrable, right? Now, because we start taking up the volume, then we can also write some notes that basically the double integral is the volume that lies above the rectangle R and below the surface Z. Yeah. Oh, why it's missing? Where is it? No. Okay. Wait for a moment. I don't know why it's missing out. I need to reconnect again. Okay. Okay, so let me rephrase that the function f integrable if the limit definition exists, and based on what we have, the double integral is actually our volume. Our volume above the region R and under the surface function Z. Okay. So I would like to focus more now on the double integral. Okay. So for the Riemann sum, the expression for the double sum, I think you can check for yourself. But I think now I will focus to the double integral and how to get into the techniques for the integrations. Okay, so in calculus 1, you have only one single integral. Now you can have double or even more, at least triple, okay, at least triple. Which if you cannot handle one, how about double? So you need to catch up, okay? I cannot review all the time, but for some part that is maybe heavily related to the techniques, I will review some techniques, but I cannot review everything, okay? But my advice, based on your midterm results, I think you know your own score. If you need to withdraw. If you're still thinking it's okay, it's on average, you can get continue, okay? Because you have other courses as well. I know the heavy coursework, but sometimes you need to sacrifice something, okay? You can think, because I think the deadline will be this week, I'm not sure the dates, 8 or 9, right? 9 of May. So you still have time before the quiz. Okay. Because if you are maybe solving the quiz and maybe the paper is empty, it means that you don't get the questions. You didn't get the questions right. Okay. So hopefully you know how to test your own self. Okay. Okay. Let me continue this part. Okay. Okay, suppose that we have these two examples. How to evaluate? So basically, let me start, maybe write some notes first. If we have, for example, let's say A, B, C, D, this is f x, y, and suppose that this is dy, dx. By default, when we have this double integral, we are going to solve the inside, okay? So we solve this, we solve this. So this is the first, and then after we get the result, so which means, this means we solve the integration of f with respect to dy, okay? So we integrate with respect to dy. We get the result, we get some equations here. We are going to integrate one more time with respect to x. And then plug in the a and b, get the result. If a, b, c, d, they are all constant, the expected result is some values. Then we can finish off the second part. That is by default, okay? The order to do the integrations. Okay, so then, based on that, we have examples now. The same surface, x squared y, when we change the order of integrations, dy dx, and that's the dx dy. They are all having the same constant, but different order. So first is y is 1, 2. This is also y is also 1, 2. X is 0, 3. Okay. So this inside integral is on y. The outside of integration is for x. So let's see what we have. So first is we integrating the surface with respect to y. So we focus on y only and treat the x as a constant, right? So just leave as it is. So we integrating y becomes half y squared, okay? So this will be, so the outside I will write just as it is. The inside will be x squared y squared over 2, and then plug in 1, 2, and we still have dx, okay? So we compute the inside Remember that this part, this 1 and 2, this is y. Let me write y equal 1, y equal 2, so you have good sense where it is. So we plug in y, which becomes 4 minus 1. Okay. Or let me write, this will be x squared. This is 2. Let me write 4 over 2 minus x squared, 1 over 2. And then this is the x. So we have, this is 3 over 2 x squared dx. And now we can integrate with respect to x. So this will be 1 over 2 x cubed. Okay. From 0 to 3. So this will be x cubed. So 3 cubed is 27. So 27 minus 0 is 27. So this will be 27 over 2. Okay. Now this is the first step. Okay. Now if we change the order, of the integrations, so first we deal with the dx first. So this will be our first integrations. So we write, so the inside will be 1 over 3 x cubed y from 0 to 3, and then dy. So let's input 27 over 3, and then this will be y, right? Or you could write, this is going to be 9y. And we can integrate, y becomes 9 over 2 y squared from 1 to 2. This will be 4 minus 1, which is 3, and we get technically the same results. And this will give you the idea that both integrations, they are correct. They are okay if we change the double integrals. Okay, this is what we call as the Fubini theorem. Okay. So as long as they are all constant. For example, we have a constant a to b for x, c to d for y, which means that they are going to be rectangle. So no matter what, we are going to take the x first and then y, or taking y and then x. They are going to have the same volume, the same results. Okay? So the double integral, this expressions equal, so a, b, c, d, or c, d, a, b, they are the same. Okay? They are the same. So you change the order of the integration, result is the same. This is valid for if the endpoints all is constant, like rectangle. Okay, now if we want to check again the double integral, let's start something very simple. Just go follow through the example here. Now we have the r. It says that x is 0 to 2, y is 1 to 2. So we can have two options. We can start with x and then y, or starting y and then x. Now maybe we start for the x dy. So we start this inside integrations will be x. So this will be, so I will integrate with respect to x, so half x squared minus 3xy squared, and plug in 0, 2, and then we still have dy. Okay. Remember that this is x, right? So plug in 2 will be, this will be 4 by 2 is 2, minus 6y squared minus 0, or maybe not need to write this, and this will be dy. And then integrating with respect to y, this will be 2y minus 2y cubed from 1 to 2. This is 4 minus 16, right? 4 minus 16. Minus 2 minus 2 is 0. So this will be negative 12. Now, notice that we have negative. So it means that it's not, it's not under the r, but it is below the r. If we draw the picture, this is going to be in the negative direction. The volume is on negative. So this might happen, and it's okay. Because if we see the function itself is a negative function. If you want to compare, you can check. If you change the order, it will be the same, negative 12. Right. Okay. Any question first? Because this is very early introduction for double integral. Okay, if not, I think I will maybe continue a little bit and then stop. Okay. Let me continue for a while, and before this average value, there is another Fubini related. So let me write first some notes here. Suppose f xy is, we can separate the functions. So we can see the function is g of x and h of y. So we have two different functions and we can separate them. And if R is a rectangular ABCD for x and y, then the Fubini we can write this is gx hy dx dy or maybe let me write first the AB gx hy dx close bracket and then dy. If we take the integral of this inside integral, we integral with respect to x, so y is a constant, right? So because y is a constant, we can factorize the h. We can factorize this outside, okay? So we can write this as this is h of y and then the dy will only affect the function of y, right? So by doing so, we can see that this is basically multiplications of these two. Okay, or let me give so the double integral gx hy dA we can write separately with each functions. We need to make sure that this g of x and h of y is truly single variable. So if you see any functions that you can see that, oh, it's separated in x and y, you can separate them and then integrate with different endpoints according to R. This is R is okay. So this is I forgot to give this part. Okay, one final note to finish off this part is the average value. If you remember average value in calculus 1, the average value is basically 1 over the distance of the interval and then integrations ab f of x dx. For the double integral, this will be very similar, but instead of the distance, we have the area, and this is double integral of fxy dA. And that's it. Finish. So chapter 15, part 1, finish. we're going to have a review and exercise later on. And also maybe for the overview of chapter 14 as well, okay? Any questions?